welcome. There's maybe only a couple of us here. That's all right. We'll do our thing. So the end of the week today, and we don't really have that much work to do, so that's a good thing. This probably will go fairly quickly. I'm not going to purposely rush, but I've only got a couple of things left to do to finish this lab. I can field questions, but otherwise I'm just going to get into it, work the lab, and then prepare ourselves, I guess, for next week. So what's left here? I pulled up lab 14. We did the constructor using an initialization list. We did the destructor, which technically is not complete because the clear function isn't ready yet. The get size function, so the clear function is waiting. We did insert, the public and the private versions of the insert. In this class, most of the actual algorithm work will be done in private functions. And then we have print in order, which is just a way to see the contents of the tree. So that's where we're at. I'm going to start with clear, and clear's easy in part because most of the work is done by the private function. So if we go down and we look at the private function, what it wants us to do is pass it a pointer to a node where the clearing process should commence from. So if we're using the public version of clear, we want the clearing, which is the deleting all the nodes, to commence from the root of the tree. So that's how we'll call that function, and we'll go ahead and finish this one before we move on. So reset, I don't know why I said reset head, that should be root. Root is null and size is 0. So this clearing will release or free all the memory from all the nodes. It will reset the root pointer to null and reset the size, the count of nodes, to 0. So all the work really is in the clear function. And I'm going to draw a picture here to sort of walk you through the thought process for clearing a binary search tree. So let me bring up my camera. Okay, so with any of these data structures that uses pointers so heavily, you always want to be careful that you're not trying to do something with null pointers. So some folks had problems on the second, what are we on, the third project. Some folks had problems on the third project that hopefully you worked out because you weren't checking for null or you weren't checking for it in the right place. So we're about to do a clear algorithm down here. And what we need to understand is that troot points to a node from which the clearing work should commence. So the first thing to check for is the obvious one, which is what to do if troot is null. Well, if the pointer that I've been given to some node in a binary search tree is null, then there's nothing to clear. So I don't operate in that circumstance. There's nothing to clear. But if troot does point to something, then I do have work to do. So I'm going to write it that way. I could write it like this. Where I have a decision element where I check for null, and in the case of null I just do nothing. But that's kind of wasted code and it can be confusing, so instead of that, why don't I just write this to be the opposite, which is if troot is not null, then I got work to do. So this is sort of checking in the opposite direction. So if troot is null, nothing will happen, and that's what I want. But if troot is not null, then I've got work to do. So I'm going to write it the way that I often see students write this algorithm, and then I'm going to write it the better recursive way. So the thing to think about when you're clearing a binary search tree is that you have to clear the root of the tree, but you also need to clear the children as well. Um, because if I just clear this part, then I'm left with these dangling children, and that's a problem because that's memory leak. So what I really want to do is actually clear out the children first and then clear out the parent. So I'll clear out the left one, and then I'll clear out the right one, and then I'll clear out the root last. Okay, so when you're developing this algorithm, we've already dealt with this situation where there's no nodes, in which case we're not going to do anything, so we're only going to operate when there are nodes, which is the not equal to null. So we can imagine this situation, but we should also imagine some other situations that are possible. So it is possible, for example, that you're being asked to clear a tree that only has one node on it and no children. It's also possible, of course, that you can be asked to clear a tree that has, let's just say, a left child but not a right child. So I'm going to write it the way I see lots of students do this, which technically is recursive but doesn't take full advantage of what recursion can do. So here's the way I often will see it done. So I want to clear the children out, and then I'll clear the parent. So what I see people do often is they'll say if troot left is not equal to null pointer, there's a child on the left to clear. So I will clear troot left. And then they'll just do a series of ifs. So if troot right is not equal to null pointer, then I will clear the right. And then I will also sometimes see people do this again, which is okay in terms of thinking the problem through. So here I am going to call clear on the left child if there is one. I'm going to call clear on the right child if there is one. And then I'm doing something kind of weird here, which is calling clear on troot, which would have been how I got here in the first place. So this one's always the weird one. Let's clean that up first, and then we'll just keep cleaning up. You're right. Thanks. Left child and right child. Good catch, Jake. Left child, right child. Oh, I've got multiples of those. Good catch. Thank you. Okay, so this is a common way that people do this. And it's not wrong. Well, I have it wrong. If I don't ever actually do the clearing work, then this is never going to resolve itself. So I know when I get to the point where I'm on this troot, what I really need to do is delete it. That's really the work of this function. So now I'm going to go through and clean it up and sort of talk about why this is all unnecessary. So the obvious one that isn't necessary is this if right here. If troot is not equal to null, well, I've already established that troot is not equal to null. So if I got here at all, it's because troot is not null. So I don't need that if, because I've already written that if. So hopefully that makes sense. That's just sort of duplicating the effort, but I do see people do that historically because they're thinking through the problem. Okay, so now this one. This one is just learning how to think recursively. And there's nothing wrong to think this way, but there's a better way to do this. The thing to think about, and I'm going to flip my page and draw a different picture, is what I talked about on Tuesday. So let me just build up a tree and put some stuff on it. Okay, so this tree is a lot scarier to consider. How am I going to clear that thing? What does it mean to clear starting here? and how does that make all these other things clear? So I'm going to put some data in here so I can refer to the nodes that I want. I'm going to follow the binary search tree rules. Put a 75 here, I'll put a 60 here, and then a 65 here. So everything sort of works. Alright, so how's this going to work? If I clear here and then it immediately checks to see if this is here and then clears it, how is that all going to work? So here's what the process would look like, and I'm going to do the stack. So the initial delete would be on 50. So a clear call would come in starting at 50, and immediately it's going to check to make sure that there is a 50 node, and there is, so that's good. And then what it's going to do is it's going to check to see if 50 has a left child. If it does, then it's going to call a clear starting on that left child. So it's going to commence the clearing process one step down into the tree. Now, nothing else can happen in this function until this part is done. So right now, the function, the whole rest of this process is waiting for what plays out once we went down the left child. Okay, so what if we're sitting here, then what happens? We check for null, okay, there is a node there, and then immediately it checks to see if there's a left child, which there is, which means that it immediately resets, recurses down the left. So now 25 can't clean itself up, and 50 can't clean itself up because they're all waiting for 15 to clean itself up. Okay, so 15 now is the sort of the root of the clearing process, and it immediately checks to see if it has a left child. It doesn't, so that first if fails. Then it checks to see if it has a right child, which it doesn't, so that if fails, and then finally it deletes 15, which means that this particular section is done, which now then allows the 25 to continue at its right child. So now it's going to check its right child. Oh, that whole other process was because it went left from 25. Now it goes right from 25, finds a null, so that doesn't do anything, and then it deletes the 25. Which means that now 50, which was waiting on what played out while it went left, can now go right. So now 50 has to go right. So 75 now takes over. Takes over its own sort of subset of the clearing process. So now it's 75 in control, and 75 has to ask the question then, am I null? Nope. Do I have a left child? Yep. So I have to delete the left child. So now 75 has to wait while 60 takes over for its portion of the clearing work. 60 asks the question, am I null? Nope. Do I have a left child? Nope. But I do have a right child, so now I have to wait for right to go. So you see how 50 still can't clear itself while it's waiting for all this work to finish. So now 65 has to check, okay, I'm not null. Do I have a left? Nope. Do I have a right? Nope. So I can delete 65. That was going to the right of 60. So now 60 has gone left and didn't find anything. It went right and cleared that subset. So now 60 can be deleted, which means now 75, which was waiting for all that left stuff to finish, can now look right, doesn't find anything, and then be deleted. And now 50, which was waiting all that time for all the left stuff to happen and then all the right stuff to happen, can finally delete. So now they're all deleted. That's the order that this would play out. But there's a way to simplify this. If you think about the fact that each one of these is really its own little subtree handling its own clearing process. So in other words, 50 shouldn't have to bother itself with what happens if my left child is there. What 50 should do is just let its left child deal with it. And what it should do with the right child is just let the right child deal with it. So we're going to play this out again just to prove to you that these checks don't need to happen. Okay, so I'm going to rebuild this tree, 50, 25, 75, 50, 25, 75, 60, 65, 15. So let's watch how this works. Without the extra checks in place. What if we took those extra ifs out? How would this thing execute? So we'd start at 50, and then we wouldn't even check. We just immediately go left. But if we go left, we find a 25 there, which is not null, so everything's okay. Now this one has gone left, but it can't go right until this one does its whole part of the process. So now this 25 section is in charge. The first thing it does is go left, which means that now the 15 section is in charge, and the first thing that it does is it goes left. Except for, what does it go left into? It goes left into a null pointer. Okay, well, what does the function do if we try to fire off the whole clearing process on null? Nothing. It does nothing. That's fine. Then it's going to have to go right, which means it's going to try another null direction. So what if we come in to clear on a null in that case? Nothing. That's fine too. So now 15 can delete itself. 25, which was waiting for that whole left side to finish, can now go right, so it's gonna, except for to the right is a null. So what happens when 25 tries to fire off the clearing process to its right? Well, it's going to try, is that null, or it's going to say, is it not null, actually, which means that, nothing happens. Well, that's fine too. Now 25, 15's already gone. Now 25 can go. And then 50, which has been waiting for all that left stuff to happen, can now start going to the right. So it's immediately going to say, okay, I need to go right. 75. Now 75 is in control, and 75 says, well, I need to go left, which is 65. 65 now is in control, but it says, well, I need to go left, except for it goes left to null. But what happens when we try to clear on null? Nothing. The function actually checks for that. If I get a null, I don't do anything, so that's okay. So that was 65 going left. Now 65... Oh wait, we already did 60. This is 60, sorry. 60 went left and nothing happened. Now 60 goes right, so 65 now finally comes into play. I'm going to have to continue this stack over here. So what happens when 65 comes in? Well, it tries to go left. And that recursive call goes to a null and nothing happens. Then it tries to go right. That recursive call goes and nothing happens. Now we're back to the 65, which sent it left, then sent it right when nothing happened. Now it can delete itself. That was 60 having gone right at that point, so now it can delete itself. That was 75 having gone left, so now 75 goes right. And it goes right to try the clearing process on a null pointer, which causes nothing to happen. And then it can be deleted. And now finally 50, which launched the whole process, had to wait for all the left stuff, all the right stuff, can finally be deleted. So they work the same. The code is way simpler. You will notice that when we drew a picture of it, the function executed a whole bunch less times for the other style. Whereas in this case, the function had to be called a whole bunch of times as it stacked up. but the code is way simpler. Way simpler. So I prefer the simpler code. Try clear right. If it goes to null, that's fine. Clear handles it, right? If this clear cycles back through recursively with null, nothing happens. Then it tries to clear right, and if it cycles back through with null, nothing happens before finally deleting troot. So that's the way I would do that. Now I'm going to go compile this. And see what we get. Mostly to see if it compiles, but if I happen to pass a unit test, that I wasn't passing before, then that's fine. And I'm going to run it with -s here, so I can see everything, passes and fails. I think I'm passing one extra. I should be failing all of the outputs because I haven't done that code yet. So if I scroll up, I am passing darn near everything. Here's an output, which I haven't worked on yet, so that's to be expected. Here's an output. So that's it. The three things I'm failing right now are output things. Okay, that's clearing. This feels really wrong. Until you get used to how recursion works, it feels like something's going to go wrong. You just sort of have to step back and think to yourself, what happens if I call this clear function with null? What happens if that is null? Well, it comes back into the function with a null here, and this protects it. It takes care of itself, as it turns out. Pretty crazy. This same setup is going to help us with printing. I'm just going to implement it, and then we'll trace it out. So print in order, we have a public one. So just like all the other functions, we have a public version which calls the private version with the root node. And I know that also just seems sort of weird and unfamiliar. But we're trying to keep the public version of our functions as simple as clean as possible, and handle the sort of nasty details of the pointers in the private functions. One of these days, though, you will use someone else's library who will not have done this for you, and you'll say, why didn't they put a public function that simplified this? What's this unnecessary extra work? So publicly, someone just says, my tree, print in order. Privately, you turn that into a, I should be putting thises on all these. You turn that into a, well, let me start the printing process for you, starting at the root node. Okay, so let's try this without having tested it first and see how that works. So the major deal breaker always is if root is null. So often you're going to end up writing something that says, well, I'm only doing something if root is not null. If root is null, I'm not doing anything. Okay, let me bring the drawing back up. So it's real simple to do this. So we've already handled the null. So if you tell me to start printing a tree and give me a null pointer, I'm just not going to do it, right? That if statement will just say it's just not going to do that. But what does it mean? To print a tree in order. What it means is that I want the data to come up to print out in ascending order. So if I were to say print this tree in order, I would print left, root, first the left, then the root, then the right, which is pretty obvious, right? So if I do the left, that's 25. If I do the right, that's 50. The root is 50, and then the right is 75. So print in order is just left, root, right. I could print in reverse order, by the way, simply by doing right, root, left. So print in order just means print the left, print the root, print the right. So I'm going to do it like I see a lot of people try to do it, and it doesn't work, but let's just start with the wrong version. So they'll end up doing something like this. Is it value or data? I forget what it's called. It's right here in front of me. Data. Same kind of idea. Nope. Center. Center comes next. Right. Which is kind of a roughing it in. So this works okay for the current tree that I have. The problem is, what if there's more stuff down here? What happens? So the way I've got the code right now, it'll just hit these three and then ignore everyone else. So that clearly is not a correct solution. What we really need to do is use recursion, of course, and this one is not doing any recursive calls. But now let's think about this. What does it mean to print the tree in order starting at the root? Well, what that means is that everything to the left, which should be smaller than the root, needs to be printed in order. That makes sense. Followed by the root, followed by everything to the right needs to be printed in order. So the flaw with this code right now is that it's not actually descending. So what I really need to do is say, well, if I have a left child, I need to recurse down to the left. And if I have a right child, I don't want to print it because that doesn't descend. I actually need all the contents down the left printed out for me in order. Now hopefully logically that makes some kind of sense. If I'm looking at 50 as my t root, what I need to happen when I get to the right is that all of these things to the right need to be printed in order. So that makes at least sense to me to say to myself, well, I'm going to cause everything to print in order to the left by recursing, and then I'm going to print the root, and then I'm going to cause everything to print in order down the right by recursing, is what we need to do. It's a little bit of magic, so we're going to trace it out here in a second. This one shows it better than some others do. But does that make sense, right? I need 15 and 25 to come out in order before the 50, and I need 75, 190 to get themselves in order to follow the 50. So left, right, left, root, right. However that happens. And however that happens, I need those in order, followed by the root, followed by these in order, to have the whole tree in order. So I can sort of just speak my way through it recursively to sort of make sense that that is what needs to happen. So how does recursion do that? So this is how people often write it, but again, if you think about print in order being a callback into this function, then I'm already handling this part for that tree. So if I just recurse to print in order, if the left child is null, then when that comes back through, this is going to protect it. It's going to be okay. Same thing for the right. I don't need that extra check because this call ends up passing the right child back into the function, which immediately checks to see if it's null or not. So the function, when I recurse to it, already does those null checks. I'm going to take the extra spaces out. So now we're going to trace the magic, which is, this helped me more than than figuring out how to code it is just figuring out what happens. So let me get back to this tree. I like the other tree better, but whatever. 25, 15. Why not put a 20 in here just for fun? Hopefully I can, where you can see it. Yeah, mostly. Okay, I'll put a 75 here, and I'll put 100 here. I'll put 110 here, and then I will put a 90 here, and then these are going to be dead ends. Okay, so let's see how this would work if I fired up a recursive print in order starting at 50. So if that's root. So if I say print in order root, it's going to start at 50. So I'm going to draw my little stack. So the first call to this function is going to come in with 50 being the root, the t root. And it's going to check to see, is that a legitimate node? It is. So it's immediately going to call a print in order, resetting the process to start at the 25. So it's going to call print in order off of that 25 node, which is going to check to make sure, is that an actual node? Yes, it is. It's immediately going to call this function off to the left of 25, which puts it at the 15. Notice no outputs have happened. Nothing has happened yet. We're just going left. Oh, and I got to go left again. I got to go left again. Yes. So now 15 is going to call this function off of here, which is null. So what happens if we try to print in order off of null? Well, if we try to print in order and I passed in a pointer to a sort of a temporary root node that's null, the if statement scrubs it off and nothing happens. So still nothing has happened. Still nothing has happened. But now that we've gone down to the left of 15, so we went left, we're going to do cout. We went left from 15, so now we're going to do cout the data here. So the first thing to pop out is a 15. And then right after that, we try to go right off of 15, which finds data, which actually is a 20. So now we're trying to print in order starting from 20, checks to see if it's null. It's not. Immediately, 20 sends this thing off to the left, which comes back null, so nothing happens. Then it prints itself. And then it tries to go off to the right. And there's nothing to the right of 20, so nothing happens. So now 20 is done. Now 15, which was waiting for that stuff to the right to happen, is done. Now 25, which is just waiting for all that left stuff to happen, can finally print itself. And then it's going to try to go to the right. And it's going to find to the right of 25 is nothing. So the if statement in the print in order scrubs that one off. Nothing happens. Now 25 is actually done. Because it went left. It went right. Now 50, which was waiting for all that left stuff to happen, can print itself. Isn't this magic? It's like magic. It's the most amazing thing ever. But 50 is not done because now it has to go off to the right. I'm going to stack them up like this instead. So now 50 goes off to the right. It's already done all of this. And it's printed itself, but now it has to wait for the right stuff to happen. So it goes off to the right, which is where it finds a 75. The 75 immediately tries to go to the left, but there's a null pointer there, so that if statement scrubs off that call to the function. Then it prints itself. Then it goes to the right. That's where 100 lives. What does 100 do? It tries to go to the left immediately, where it finds the 90. The 90 will go to the left immediately. and find nothing, so that one's done. It will then print itself. So 75 comes after 90. Prints itself, and then it tries to go to the right where it finds nothing. At which point it's done. It did everything it was supposed to do. Now the 100 was waiting for the 90 as having gone down the left, so now the 100 can finally print itself out. And then it tries to go to the right. So what happens when the 100 goes to the right? It hits the 110. The 110 will try to push it to the left and find null. Nothing happens. The 110 then prints itself and then tries to push off to the right where it finds null. And now the 110 is done. Now the 100 was waiting for the 110 is done. Now the 75, which was waiting for the 100 to finish, it's done. And then the 50 is done. So the 50 had long ago printed itself, but it wasn't actually completely finished until all of that right stuff happened. And what you end up with is 75, 90, 100, 110. They come back out in order. It's friggin' amazing that it works that way. But if you draw some pictures, which I just will constantly recommend, it may help some of you come to understand how this recursive stuff works. But at first it's like magic. After a while it will seem like the obvious thing that should happen, but at first it is like magic. I'm going to compile and run that, see where we're at. And now we're passing everything as expected. That takes a lot of getting used to. We're going to do a bunch more of these. All I can do is encourage you to take the time to like draw yourself a tree. Like go through, just make up a bunch of numbers, you know. And then I'll shut up. But do this kind of thing. Just make up some numbers. 42, 19, 73, 18, 4, 5. It doesn't have to be that many. And then insert them in your head into a tree. So if I insert the 42, that becomes the root. And if I insert the 19 after that, well, that becomes the left side of the root. If I insert the 73, that goes to the right of the root. The 18 is going to go left of the root, left of the 19. The 4 is going to go left of the root, left of 19, left of 18. And then the 5 is going to go left of the root, left of 19, left of 18, right of the 4. So this is the place to start. Trees, binary search trees can look all ginky like this. It just matters. It depends on how the data comes in. If you're going on in your computer science studies, the next level from here is to make these trees balance themselves out, which is other algorithms. But they can be sort of all out of whack and unbalanced like this. And by balanced, I mean what you really want is a tree that as much as possible is not hanging heavy anywhere. See how much more balanced that is than this one. This would be what comes in programming algorithms 3 if you go that far. But for now, we have a binary search tree and it can be all wacky like this. So you do this, and then you see how print in order would work on it. Right? See if you can trace out how that's going to work with a print in order. I mean, intuitively, you know that it should print the numbers in ascending order from the smallest to the largest, but see if you can draw a picture for yourself of the order in which the functions are being called. Who's the t-root, or is the t-root null, because that function is going to be called on all these null dangly spots. And if you wrote a good algorithm, then all that happens is nothing. So when you try those kinds of experiments, it doesn't take very long, and it can help to come to some understanding of how these trees work. The algorithms next week get more difficult, so just heads up about that. They get harder. Okay, I am done. I'll sit here for a few minutes and just wait to see if there's any questions. Otherwise, I will see you on Tuesday next week at 11 a.m. Have a good weekend if you're checking out. Thanks for being here for the live part. It's nice to have at least a few live bodies on the other end of the video, so I appreciate it. Thanks for catching that bug in my code too, Jake. Good catch.